Hi, this is Babak. In this video I'm going to solve the following problem for you. This is a problem in linear algebra on the topic of lines and planes in 3 space. Let me read the problem for you first. Let A with coordinates 2, 0 and 0, B of coordinates 6, 0 and 3, and C of coordinates 2, 4 and 0 be the vertices of the triangle ABC. Determine a parametric equation of the line on which the internal bisector of the angle A lies. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do it correctly, one possible answer to this problem would be this equation. X, y, and z is equal to 2, 0, and 0 plus t times 4, 5, and 7. Okay, now let me solve the problem for you. Let us sketch a figure for ourselves to understand the problem better. So for example, assume that this is my triangle ABC, and then let me just name it A, B, and C. My goal is to find an equation for the line on which the internal bisector of the angle A lies. So for example, assume that this is the angle bisector here, so I will try to do my best to draw it good. So this is assumed that this is your angle bisector here. Let me call it D. It means that this angle and this angle are equal. Okay, and then I want to find an equation for the line, this line for example, on which this line segment AD lies. Okay, so in principle, I want to find the equation for this line. And you know that the strategy of finding an equation for a line, I need two pieces of information. One piece is I need to find a point on the line, which of course you see that A is a point on my line. Yeah, so that is good and that's enough for my purpose. But then of course I need to find a vector that I can convince myself that is parallel or lies, of course, doesn't matter here, on the line that I am interested in writing its equation. This is absent here, so I need to understand how to find that. Okay, but then something is clear. Let me just review a little bit about vector addition. Okay, so if I have two vectors that they start from the same point, say let us having this vector u, and I have another vector, for example, from the same point, vector, let me make it a little bit shorter. Okay, so assume that I have these two vectors, u and v. You know that if I want to add them, one possible way is to complete the parallelogram that I can construct on these two vectors. Namely, I can draw a line parallel to this vector from the end of this vector and do the same thing from here, and whenever they cut, then this means that I have my parallelogram, and then I can connect this to this opposite one. This becomes the vector u plus vector v. Of course, there is no guarantee that this vector u plus v bisects the angle between the vectors. For example, it is clear in this picture that this vector, this angle is smaller than that angle. Yes? But if the vectors that I start from have the same length, then this parallelogram actually becomes a rhombus in practice. Okay, so what happens if I have, for example, let us consider this case. Let me consider this to be vector u, and then let us try to draw something exactly 3 units here. So hopefully this is good. Let me consider this one to be vector v. Here I am assuming that these two vectors are of the same length. And then if I do the same thing, meaning I complete the parallelogram, in this case, the parallelogram is actually more specific than that, and it becomes a rhombus. Yes? In that case, we know from the geometric properties of a rhombus is that the diagonal is also the angle bisector between these two sides. Okay? So this is what I can use here. But of course, there is no guarantee that these two as vectors have the same length, so I cannot add them. So if I add them, there is no guarantee that this lies here. Actually, in this picture, it doesn't. So I need two equal vectors, one on AB, not equal, I need two vectors with the same length, one in AB, on AB, and the other one on AC. Okay, so the famous vector would be the unit vector lying on AB. So if I find the unit vector on vector AB and the unit vector on vector AC, and if I do the addition using the parallelogram law, because of what I described here, this parallelogram becomes a rhombus, and then the addition of these two vectors would be on the bisector of the angle between two vectors exactly. But the angle between these two vectors is exactly the angle A itself, because one of them is on AB and the other one is on AC. So that's it, and I have my direction vector and I can solve my problem. But how can I find the unit vector on AB? This is a standard in linear algebra, yes? So what I have to do, first, I determine vector AB by, for example, B minus A here. So what is B? B is 6, 0, and 3, minus A is 2, 0, and 0. So this gives me that vector AB is equal to 4, 0, and 3. This is my vector AB, yes? And now, if I want to find the unit vector here, so for example, let me call this unit vector. Let me make it, so for example, assume that this is the unit vector. I call it unit vector E1. If I want to find unit vector E1, you know the recipe. What I have to do, I need to calculate the magnitude of my vector, the norm of vector, and then calculate its reciprocal and multiply it by the vector itself. But from here, it's very easy to calculate the length of the vector. So the norm of this vector AB is equal to square root of the first one to the 2 plus the second one to the 2, third one to the 2, which is equal to 5. So this means that this becomes 1 over 5 multiplied by 4, 0, and 3. So finally, I got one unit vector, which is equal to 4 over 5, 0, and then 3 over 5. Yes, so this is one of my unit vectors. I do the same thing for finding the other unit vector, which I call it E2, and I assume that this is, so I need to draw them with the same length. Okay, assume that I have done that, and this is E2. Okay, so how to find E2? The same process again, yes? So I do E2 by calculating AC first. So AC is C minus A, which becomes, here in this problem, C is 2, 4, and 0. And A is the same to 0 and 0. So this implies that vector AC is equal to 0 and 4 and 0. This is your vector AC. But now you need to find its magnitude. So the magnitude of this vector is equal to square root of, as before, 0 to power 2, 4 to power 2 plus 0 to power 2, which becomes equal to 4. And then if I want to find vector E2, this becomes 1 over norm of AC multiplied by vector AC. So it becomes 1 over 4 multiplied by vector AC, which is 0 and 4 and 0. But then if I multiply that, E2 becomes 0 and 1 and 0. So this is exactly the J vector, but that's a coincidence. Okay, and now what I do, if I add them, So if I add them here, this vector that I construct in this case, because this becomes a rhombus, this E1 plus E2 will play the role of my direction vector for this line that I am looking for. So I would say that the direction vector D that I am looking for is nothing except this one. Of course, this is one of the possibilities, but one is enough for me. So then it becomes what? It becomes 4 over 5, 0, 3 over 5, plus 0 and 1 and 0. So this becomes 4 over 5 plus 1 and 3 over 5. Of course, I can choose to work with this one, but usually to get rid of fractions, I rescale this d by multiplying it by 5. And I hope that you understand the geometry here, because if I multiply this by 5, what's happening? I am increasing the length of my vector, but still it lies on the same direction, on the same line segment AD, so it still can play the role of my direction vector. But that's up to you. You can work with this one. But I would prefer to multiply it by 5. So for example, I would say that d prime is also another direction vector that I multiplied by 5. So it becomes 4, 5, and 3. Yes. So I realize that might be I have made a mistake in that calculation, or I have done some wrong thing here. Let me quickly double check. So AC is C minus A, so that is right. And then the length is 4, so that is correct. And then I have AB, which is the difference between these two. That's also correct. So what I have done is correct. When I add them, yes, that's the middle term. That is, yeah, so that's correct. So I have done probably a mistake here. So this is actually the direction vector. So what happens is this. So I have x, y, and z equals to 2, 0, and 0. These are the coordinates of vector A, the point A, and then I will write it as plus my parameter multiplied by 4, 5, and 3. So this is the correct answer. Sorry, I should have made a mistake when I wanted to calculate this before. So this should be 4, 5, and 3, not 7. Okay, below this video you will find the link to the PDF file of these notes. I hope that this video is useful for you. Until the next video, be safe and goodbye.